In this video, I want to talk about two examples of whether or not a series converges. So for the first example, let's look at S, a sum from n equals 1 to infinity of square root of n to the fourth minus 1 over this complicated thing, 3n cubed plus 4 plus e to the minus n plus 1 over n. Okay, so what are we noticing? Our an, so this will be an, is given to us as a ratio of things. And remember, let me write this a little clearer. So it's a ratio of things. And remember, the ratio test is good for ratios of things when there's going to be a lot of cancellation when you divide an plus 1 over an, but so is the limit comparison test. And what's nice here is that in the numerator and in the denominator, the largest term is some power of n. Here we have a square root of n to the fourth. Here we have a 3n cubed. 3n cubed is much bigger than 4. It's much bigger than 1 over n. It's much bigger than e to the negative n. So the idea here is because we have a ratio of terms and we can identify the largest thing in the numerator and the denominator, is we're going to apply the limit comparison test, and we're going to let Bn be the ratio of the highest terms, highest powers of n, in the numerator and the denominator. So highest powers in numerator and denominator. Okay, so what does that mean? So we're going to let Bn be equal to square root of n to the fourth divided by 3n cubed. So you could just take n cubed instead. I like taking the whole term, 3n cubed, rather than just the power. Because now, the whole idea of the limit comparison test is we have to be able to say something nice about this ratio, an over bn. But an is equal to square root of n to the fourth times square root of 1 minus 1 over n to the fourth, divided by 3n cubed times 1 plus, and now this is going to be sort of a mess, 4 over 3n cubed plus 1 over e to the n, that's e to the minus n, and then we also have in the denominator 3n cubed, and then plus 1 over 3n to the fourth. We're going to take all that, we're going to divide by bn, which is this ratio, square root of n to the fourth over 3n cubed. Okay, so what is this ratio equal to? Square root of 1 minus 1 over n to the fourth divided by this whole thing right here. 1 plus 4 over 3n cubed plus e to the minus n over 3n cubed plus 1 over 3n to the fourth. What these terms are doesn't really matter, because as n gets really large, they're all going to 0. We see that the limit as n goes to infinity of an over bn is the limit as n goes to infinity of this whole quantity. And this is 1 square root of 1 minus 0 over 1 plus something going to 0 plus something going to 0 plus something going to 0, which is 1. So what does the limit comparison test say? When the ratio of an over bn approaches some real number c not equal to 0 and not equal to infinity, something like 1, then the an series converges if and only if the bn series converges. Okay, so how do we decide whether or not the bn series converges? Well, the sum from n equals 1 to infinity of bn is the sum from n equals 1 to infinity of square root of n to the fourth is n squared, right? Square root of n to the fourth is n squared, 3n cubed, which is a sum, n equals 1 to infinity, of 1 over 3 times 1 over n. We can factor out this 1 over 3, and this, what we're left with, is a p series with p equals 1. So let me just erase right here because we're done. This equals 1/3 sum n equals 1, infinity, 1 over n. And this is a p-series with p equals 1, so the whole thing diverges. So the Bn series diverges. The limit as n goes to infinity of an over Bn is 1. So S also diverges by the limit comparison test. All right, so the key idea was that we decided to use the limit comparison test by seeing that we were given a ratio of things where we could identify the highest power of n in the numerator and in the denominator and set Bn equal to that ratio. So I'm going to pause and erase, and we'll do one more example. For our next example, let's look at a sum from n equals 2 to infinity of minus 1 to the n minus 1 over square root of n minus 1. Okay, you can rewrite this a little bit, if you like, as a sum from n equals 2 to infinity of minus 1 to the n minus 1 times 1 over square root of n minus 1. This part here, this is always positive. N starts at 2, so the smallest this denominator gets is 1, rather than like 0 if n was equal to 1. But this minus 1 to the n is a great sign that this is an alternating series. Minus 1 to the 2 minus 1 is minus 1. So these terms go negative, positive, negative, positive, negative, positive. So this is an alternating series. We can set the non-minus 1 to the n part as Bn. And now all we have to do is check, is Bn decreasing? And then is it true that the limit as n goes to infinity of Bn equals 0? If both of those things are true, then this series is going to converge by the alternating series test. Okay, so how do we check that Bn is decreasing? Well, you could set f of x equals 1 over square root of x minus 1, and then compute the derivative and see that it's negative. But you don't really have to do that here. All you have to do is note that as n gets bigger, square root of n is getting bigger, so square root of n minus 1 is getting bigger. So the denominator is getting bigger, which means that Bn is getting smaller. So you don't have to do this whole first derivative test part here, but you can get away with doing something a lot simpler. And now the limit as n goes to infinity of Bn, well, that's a limit as n goes to infinity of 1 over square root of n minus 1. And as n gets really large, square root of n gets really large, and square root of n minus 1 is still going to infinity. So this is 0. So that's it. So S converges by the alternating series test. So again, I just want to emphasize, the alternating series test is only useful when you have an alternating series, but when you do, it's generally pretty easy to apply.